move on to the data-driven linear analysis of turbulent flows from Stanford and Herrmann.
Thank you very much, Salvador. So I am McKeon from the University of Chile, and this project was developed with Steve Brunton from the University of Washington, and also McKeon. So, all right, let me start with the big picture. The main objective of our project was to develop a data-driven method that is able to take in turbulent flow simulation data and allows us to perform mean flow-based stability or resultant analysis as a post-processing step on that data. So to achieve this, we developed a new method that we're calling nonlinearity subtracted DNT, or NSDNT, that works following some simple steps that I will explain now. So the first one is to run a DNS or a DS, and we know that the flow field that we get will be evolving according to some underlying governing equation. That's what our solver is approximating. Okay, so if this is an incompressible flow, you prime the velocity perturbation field. In that case, L will be the mean flow linearized operator, and N here are the nonlinearities, which we call the nonlinear forcing in the resultant framework, although here it's in the time domain. Okay? So up to this point, there is nothing data-driven. This is just the physics that we know, that we can express in this form. We then collect snapshots of our velocity field, right, in this data matrix X, and we can also collect snapshots because we're doing simulations. We can ask our solver to output or output quantities that allows us to compute this field. So this is just a field, and we get a time sequence of the field. We collect those on a second data matrix Y. And we then do a DMD-like regression to find a best fit, low-rank linear operator that maps X to 1. And the key difference with DMD is that because we're subtracting the nonlinear forcing here, we know that the operator that we get is an actual approximation of the mean flow linearized operator. So that's how we know that what we're getting is connected to the governing equations. That's the key difference, and that's what allows us to then use the low-rank representation that we learned to perform linear analysis. So what I'm showing here is the application of this method to DNS data of a minimal channel flow. So this is the leading resultant gain for one wave number supposed the channel flow. These are eigenvalues, and in blue you see the values learned from data, used from the DNS data using NSDNT, and in gray you see the equation-based context. And because this is the CTR summer program, we said, well, let's apply this to a full aircraft. So, this is the setup for the flow over the JAXA standard model that was implemented by Conrad Webb. Around there. Nice to meet you. So, what you're seeing here are isosurfaces of string-wise velocity perturbations. And this is, as I said, the flow over the JAXA standard model, the Reynolds of 2 million, low Mach number, and angle of attack. And so we took this data. We have been gathering snapshots throughout the 4 weeks, basically. And we developed a framework to scale this method to be able to apply to some complex geometry. So from the data, we learned a low-rank representation of the mean flow linearized operator, and we used that low-rank representation to perform resultant analysis. So in this case, discounted resultant. So this is the leading resultant gain as a function of Schuhal number, and this is the most amplified response mode that we got, and its corresponding force. So the main development that happened during the program is that we were able to scale our preliminary implementation of the method to be able to do this tri-global analysis. And one thing that I want to point out is that what's practical about this NFDMD method is that we can perform this analysis in a very non-intrusive way. So we can actually apply this with data that we get from commercial codes or legacy codes that can be hard to intervene. And in principle, we think that it should be straightforward to extend this method to complex multi-division flows, because all you really need to know is what's the structure of the nonlinear part. that you can subtract it out. So if you can output the nonlinearity from your solver, then you can apply this method and perhaps do this analysis that would be more involved by developing a new linear solver. And I want to end by acknowledging the support and resources provided by some program, because probably this project would not have been possible without the support. So, thank you.